Hello, everybody, and we're going to start discussing the Big Bang today. Take a moment to think here. It was not that long ago that questions about the origin of the universe were truly considered unfit for scientific study. Now, that all changed with Edwin Hubble's discovery that we're going to talk about here in a minute. But I thought we'd start today's discussion off with a paradox. And if you remember a little bit about what a paradox is a proposition, an idea that despite sound or apparently sound reasoning, starting from acceptable ideas, leads to a conclusion that seems kind of senseless, like unacceptable logically, like almost self-contradictory. Uh, it, it results in something that just doesn't make any sense. So let's dive in here to Olbers. Now, Olbers essentially what he wanted to know was, why is the universe cold and dark? Now, on the surface, that seems like a pretty silly question. We all know the universe is mostly cold and dark out there. Um, but what he was getting at was, if you consider the universe uh, to be an infinite static thing, and if you were to look out into it, then every direction that you look, your eyesight should land on the surface of a star. Okay? The whole sky, in that respect, should be as bright, literally, and as hot as the sun, even at night. So we shouldn't have any nighttime. It should just be hot and bright all day long. In fact, we should be essentially on fire because of the radiation permeating our universe. And it seems kind of strange because obviously it isn't that way. So if we look at number one here, Olber's paradox is a paradox, and to describe it, his paradox essentially asks that, in an infinitely static universe where there are infinite numbers of stars, no matter where you look, you should see a star. And if that's the case, everything should be just as bright and as hot as the surface of the sun. Now, the paradoxical point is that it's just not that way, right? That's why it's a paradox. So something's wrong here. Paradoxes oftentimes lead us to some really surprising discoveries in science. So that's why we like to look at them, not because of the fact that we just don't know or we can't figure it out, but paradoxical thoughts tend to reveal things to us in science. Now, to kind of continue with Olbers here, uh, he was talking about stars, but today we know that the stars that we see are actually all relatively close by. Most of the stars we look at are right here in the Milky Way galaxy, right? So, to put it in more correct terms in modern day, every direction you look in the sky, your eye ought to land on a galaxy. And because the universe is infinite in size, there's so much light out there from all those galaxies, we ought to pretty much just be burnt alive. And we all know that's not the case. So let's dig a little bit more deeply into this and try to look at what Olbers thought was the correct explanation to this. Now, this is not correct. Olbers thought to himself about this quite a bit, and he came up with the idea that clouds of interstellar dust, gases out there, dust, were absorbing the radiation, and therefore it wasn't getting that hot. Like, all the light wasn't making it to us because there was stuff in the way. Now, we know there's stuff in the way for a lot of light, but if you consider this fact, this is not correct. Like, this doesn't work. And you can very quickly realize that, because if there's gas and dust in the way, that stuff's just going to heat up to be as hot as the stars themselves and the radiation that's hitting them, and so we're still all toast. And we know that's not the case. So this doesn't solve the paradox, but it was Olber's best stab at a fix. So that's the answer to number two there, if you're looking at your papers. Uh, let's kind of take a little bit closer look at our modern understanding of why this just isn't so. And some of you may have already come up with the reasoning yourselves because you know a little bit about the universe. The first point we need to understand is that the universe isn't eternal. In other words, infinitely old. It's not static. By static, we mean sitting still. And we talked a little bit about this idea of infinity. In other words, infinity means like forever and ever and ever without end. And the age of the universe is not infinite. Olbers didn't know that. Its size, however, could very well be infinite, right? Those are two very different things. Um, so to discuss his problem, though, we have to grapple with the idea that the universe is not infinitely old. It hasn't been here forever, and it's also not sitting still. So uh, what that causes is sort of a couple effects here. First of all, the light from the farthest stars away hasn't actually had time to even reach us yet. So don't try and answer this question yet, because I'm going to put it in simpler terms for you. Okay, we'll talk again about lookback time, but we already discussed that. The time to see that light, the time it's taken that light to travel, is actually greater than the age of the universe. So there's some things that are so far away from us, say galaxies, right, that the the time that the universe has been existent for is not long enough for that light to have actually reached us yet. Remember, the speed of light is finite. It's a precise number. It's unchanging. It's a constant. So if the speed of light is constant, it takes a certain amount of time for that light to get to us. So therefore, the farther away something is, the more time it takes the light to get to us. If the universe is bigger than the time required for the light to get to us, well, it hasn't got to us yet. Oh boy, talking in some crazy circles here, aren't we? So the final piece of the puzzle here comes from the fact that we now understand that the universe itself, the fabric of space and time, is actually expanding. Okay, and what that causes is a reduction of the energy in the emitted light via redshift. So remember back, we talked about redshift some. We talked about the Doppler effect. This is the Doppler effect essentially caused by the expansion of the universe itself. So the universe expanding can cause the Doppler effect. And in light, the Doppler effect isn't sound, right? The Doppler effect is light shifts colors. Another way to say that is light shifts energies. So the energy of the light changes, it gets stretched out. If you will, think of it like this, and we'll come back to this again later, but think of a string, if you will, that's kind of twisted up like a wave, like so it's got rises and falls, it goes back and forth, back and forth. If we take the two ends of that string and pull on them, we stretch the string out, right? What happens to the peaks and the valleys of that string? Well, they become less, right? So you can think of the energy as the peaks and the valleys. As the string gets stretched out, the energy gets reduced. What happens to the distance between peak to peak? Well, that becomes longer, doesn't it? We just stretch the peaks out, so it's further from one peak to the next peak, and that's what happens to the light is it becomes shifted towards the red end of the spectrum. It becomes more red. Okay, so for example, if we take the extreme levels of radiation from the Big Bang itself, which we're going to talk about here in a moment, Olbers didn't know about this, of course, they have been redshifted all the way into the microwave regions of the spectrum. And we'll talk more about that in a second here in the cosmic microwave background radiation. So, to answer number number three, explain the accepted line of reasoning that resolves Olber's paradox. Our accepted reasoning here, what we understand, is that the universe is not eternal. It's not infinitely old. It might be a better way to say that. The universe is not infinitely old, and it's not static. And because of that, the light has been shifted to a lower energy level. Because the universe is expanding, the light has been shifted to a lower energy level. Now, it didn't change the speed of light, but it shifted the frequency of the light. Okay, so hopefully you've got something down for that. Let's kind of move along here. So, and I'll kind of re-summarize that again for you. The universe, if you think this through, must have had a beginning. In other words, it's not infinitely old, and it must be expanding, or we'd all be on fire, right? We'd be burning up right now. And that's truly not the case. So we have resolved Olber's paradox, and this is just another way of saying the same thing. You're welcome to use this for your answer. I kind of like the cartoon over here. I think it's pretty pertinent to today's time. the universe, we got a guy standing up here in a suit and a tie there, and he's discussing this with, assuming a astronomer there who's looking quizzically onwards at him. And he says, the universe is expanding faster than ever, and I don't even feel a breeze. And she's looking at him like, what's wrong with you? Well, I think that sometimes we get screwed up with science. We don't understand science, and we get confused about what we mean by the word theory, right? In today's society, we have a big problem with people misunderstanding that word, and we assume that just anybody could have a theory. I've got theories about all sorts of things, like an idea about something. That's vastly different than a scientific theory. Remember, we talked a lot about this at the beginning of the year. Scientific theories are fundamentally different than somebody's random idea. They are not on the same footing at all. So when we start to think about how to do things, and we think that a theory is just as good no matter who came up with it, it's just not true, right? A theory, an idea that you have, is not the same thing as a scientific theory. And I think we run into a lot of problems with that because most people just don't understand that. We also are talking today about what we call the Big Bang Theory. The Big Bang Theory is supported by a tremendous amount of evidence and information backing it up. In fact, it is our only and best explanation of how the universe came into being. And it's a big one. There's a tremendous amount of information backing this thing up. Hopefully, by the time we're done here, you'll recognize that it's not just a theory, just like the theory of gravity is not just a theory. It's not. Nobody's found a way to disprove it. It's a very powerful thing. It's not just somebody's wacky idea. So let's turn to the man himself, Edwin Hubble. So Edwin Hubble is the guy who discovered that galaxies are all moving away from each other. So this is the discovery right here. This was the evidence for the Big Bang, and it was really what launched the field of cosmology. And I think that's the answer to number 4 there. The guy who discovered the field, who made the discovery that created the field of cosmology was Mr. Edwin Hubble himself. And Hubble's discovery that the galaxies were all moving away from each other gave us a hint that the universe was expanding. And if we ran this backwards and rewound this, we'd come to find that at earlier times, galaxies would have been much closer together. So think about how big of a deal this is for just a moment, right? Before Hubble's discovery, it was just assumed that understanding the formation of the universe really fell to the realm of religion and spirituality, because there was no way to scientifically test anything. There was no scientific information about it that we could glean. And Hubble really changed all of that. And it launched this new field called cosmology. Not cosmetology, right? That's the putting on of makeup. So no discussion of cosmology would really be complete. No discussion of the Big Bang would really be complete without mentioning this guy right here, right? Sir Frederick Hoyle. So Sir Frederick Hoyle, British astronomer, he coined the term the Big Bang, and that's the answer there to number 5. He coined the term the Big Bang in 1949, apparently mocking what he somewhat considered an insane hypothesis that out of the entire universe, our entire universe expanded out of a single, unimaginably hot, dense singularity. Okay? Remember, this is wrong. Fred Hoyle was wrong. Now, Fred Hoyle was not some idiot guy off the street who just had no idea and was like, oh, I've got a theory that's better than that. I've got a better idea. Fred Hoyle was a famous astronomer. He was knighted. Sir Frederick Hoyle, right? This guy made a lot of important discoveries. He was a big name. So when he stood up against this idea of an expanding universe, or a universe starting out of a singularity, it made some big waves in the scientific community. Remember, scientific theories have to survive a lot of tests. They get attacked by other scientists. It's not easy for a theory to survive. They have to prove themselves out. And the Big Bang, it took some time for it to prove itself out. There's just some initial data right here. And Fred Hoyle knew about this data. So let's talk about that for just a second here. Uh, why did Hoyle dislike the idea of the Big Bang? And it's really kind of interesting. Historically here it's interesting because if you know anything about this, Fred Hoyle, he didn't dispute Hubble's data, right? He really just didn't like the interpretation. Now, a lot of times in science, there's a lot we can learn from this. There's many different ways to interpret a set of data. Now, don't fall into the trap of thinking that, well, there's no scientific theory is ever really going to be right because there's just multiple ways of always interpreting it, right? Like people say this all the time about climate science. Oh, well, that's just one interpretation of the data. There's lots of ways to interpret the data. Well, hooey, there's not lots of ways to interpret the data all the time. Sometimes there are, right? But eventually, you collect enough data, you make enough discoveries that you say, this is the best explanation of what we've got. Everything else doesn't hold up. Well, this is early on in the whole theory of the Big Bang. And maybe we should really call it more of a hypothesis at this point to be more scientifically correct with it. But scientists screw that word up all the time too. So what are we going to do with that? So anyway, what did Hoyle dislike about this? It wasn't that he disputed the data. It's that he felt that the idea of the universe having a beginning was fundamentally unscientific. That it was somehow an appeal to the universe having to be created by a creator. Now, that's really interesting when you think about the fact that many religious individuals have a lot of trouble with the Big Bang theory. They dislike it because they feel that it removes the need for a creator. Now, here's a scientist saying, I don't like it because it is just assuming like there could be this creator in science. So it's really kind of interesting how this whole thing plays out. But anyway, he puts forth this idea. Well, let me make sure that you get one here for number 6. What did he dislike about the Big Bang? He thought that it was unscientific because he thought it was really appealing to the idea of a creator. In other words, if the universe had a birthday, a date that it was formed, then we're appealing to a creator. So that's what Hoyle didn't like about it, okay? Because we know that in science we don't appeal to religious explanations for things. Well, that's not at all what the Big Bang Theory was putting forth, but he felt that was one of the problems with it, okay? So he puts forth his idea, and this is the answer to number 7 here, of something called the steady state theory. And you don't hear anything about this anymore because scientists have long since dropped the notion, and even to call it a theory at the point that he put it together was really wrong. I mean, it really was a hypothesis. There wasn't a tremendous amount of data backing it up. It was just one way to try and explain the facts that we saw in the galaxies moving apart, right? The facts that Hubble discovered. So his steady state theory, what it did was it tried to explain that data by creating an unchanging eternal universe. Okay, in other words, he tried to keep the universe steady in its state, an unchanging eternal universe where the only way he could explain the data from Hubble was to say that somehow galaxies are appearing to move because new galaxies are being formed in between them. Okay, there's a lot of problems with that, aren't there? Right? So make sure you get the answer there. The steady state theory tried to explain the data by postulating, by stating that galaxies seem to be moving only because new galaxies were being formed in between them. Okay, so think that through. There are a lot of problems with that, and obviously scientists noticed that very, very rapidly. If you're going to have galaxies appearing in between the other galaxies, well, then you ought to have some way to explain how the galaxies are suddenly appearing. What are they forming out of? What's making them? And so that became a big problem. There were other problems too with it, and eventually it was completely dropped. And according to Hoyle, he really wasn't trying to make fun of the Big Bang Theory when he made that statement. He created the term. Um, I kind of doubt that, but anyway, he said he wasn't trying to make fun of it. He was just trying to show it in contrast in how strange it was in terms of an idea. But the name stuck, and here we are with the theory called the Big Bang Theory. So, moving along here, a new discovery happens, and this is a tremendous one. This one's pretty big. Arno Penzias and Robert Wilson of Bell Labs received the Nobel Prize in 1978 for making this discovery. And you watched the movie that we showed, and they talked about this quite a bit. There they are with their telescope. It's a funny looking telescope, isn't it? It's really a big detection device to detect microwaves that they were trying to bounce back from the Telsat satellite from Bell Labs. They were trying to communicate with the first satellite that was basically creating cell phones. This is where it all kind of started. Look at that. It's kind of funny, isn't it? They're pretty different than a modern day cell tower, right? So these things are communicating with the satellites up there. And that's the answer there to number 8, who received the Nobel Prize. Sorry, I'm having a hard time here. A cat just crawled on top of me, and I can hardly move. So, Penzias and Wilson, the two guys from Bell Labs. Now remember back to the video, they actually thought that it was that their initial data was being caused by some anomaly, and they tried to rule every darn thing out. They just had this background hiss, this noise that made it very difficult to communicate with the satellite. And so they even went to the extent of climbing into the bell up there. The right-hand side of that thing is actually all open with a ladder, and getting brooms and dustpans and essentially sweeping out all the pigeon crap and shooing out all the pigeons that were in the antenna, thinking maybe the pigeons were actually causing this. And they just failed to track it down. Didn't matter where they pointed this thing, they heard the same noise, the same radiation everywhere in the sky. And then that's when they called up, I think it was Cal State, and talked to the folks there, and were like, oh, you guys are actually looking for this stuff. Guess what? We discovered it. We get the Nobel Prize. To this day, I think it was Wilson who said, hey, I don't even really feel worthy of this because I just kind of stumbled upon it, right? Like, wasn't trying to make a discovery, but sometimes that's the way it works out. So they get credit for that. All right, let's look at the electromagnetic spectrum here for a second. We talked about this some, and there's some confusing things we're about to delve into here. Remember, the background radiation from the Big Bang was tremendously hot. It was very, very hot. 3,000 Kelvin. All right, so Kelvin is a different temperature scale than we have compared to Celsius or Fahrenheit. At 0 Kelvin, that's the temperature at which molecular motion theoretically ceases. In other words, molecules stop jiggling at 0 K. Initially, the Big Bang is really, really hot. In fact, much hotter than 3000 K. But we'll get to that here in a second, okay? Let's just kind of look at how this plays out. So at 3000 K, that's a lambda max, which is the wavelength of maximum emission of the radiation. So in other words, where does it peak at? Of 970 nanometers. So if you look over there on the right at the electromagnetic spectrum, 970 nanometers, I believe, puts us somewhere around the infrared region of the spectrum. Okay, so that's heat radiation. And today, when we look at this same radiation from the Big Bang, it's at only 2.735 Kelvin, right? With a wavelength maximum, a lambda max, of 100,000 nanometers. Now, why did that number get bigger? Because the light got stretched out. Remember, when you stretch it, right, it's going to reduce its temperature, and it's also going to increase the distance between the waves. So the wavelength actually got bigger, which means redder. Well, redder than that, redder than infrared there, if you keep going down the spectrum, delves into the microwave region of the spectrum. And today we measure that wavelength at essentially 1 centimeter radiation. and 1 centimeter radiation falls squarely in the microwave region of the spectrum. So the answer to number 9 there is that we are in the microwave region of the spectrum with the radiation that initially started out in this scenario at somewhere near the infrared. So that's the answer to number 9 there, in the microwave region of the spectrum. We're going to talk here a little bit about where that 3000 K comes from, but just remember it's getting stretched out. That's the whole point here, okay? So we're in the microwave region of the spectrum. Okay. Let's discuss look-back time here. Okay. Oh, I missed current temperature of the background radiation. Back her up here again really quick. So our current temperature is 2.735 Kelvin. Okay. Current temperature there for number 10 is 2.735 Kelvin. Okay. Number 9, we're currently in the microwave. A little bit into the short radio waves, but microwave, that's why we come up with the idea of the microwave background radiation, right? That's where it gets the same. Okay. There we go. Let's discuss again here look back time. Okay. Think back to, we've already talked about this some. This is the Andromeda Galaxy, beautiful galaxy. If we throw Earth on here, the look back time for the Andromeda Galaxy is about 2 million years. So what we're saying is that the Andromeda Galaxy is so far away from us that any light coming from it has taken 2 million years because of the speed of light to hit Earth. So if the whole galaxy somehow vaporizes tomorrow, it will be 2 million years before we see that event actually take place, because that's how long it takes the light to get to us. So this is important because it definitely concerns the Big Bang. So remember, the Big Bang occurred a long time ago, right? Nearly 14 billion years ago, 13.8 billion years ago. So when looking deep into space, the light from galaxies we see has left them from a long, long time ago. The time it takes the light to travel to us is what we call the look back time to that galaxy, that star, whatever it is we're looking at. Okay? The equation that shows this, that explains this, is very, very simple, and this is the answer here to number 11, and I'd like you to label the variables, don't just write some letters down. T, the time equals d, which is distance. Time equals the distance divided by the speed of light. That's what c is. Okay, remember the speed of light is constant, so drink that in for a second. Okay, the look back time is the distance to the galaxy that we're concerning us divided by the speed that light travels. Okay, so it's it's a simple equation. It's the same equation you would use to figure out how long is it going to take, or what's the time it's going to take for a car to reach you if the car is, say, I don't know, 300 miles away and it's traveling at a speed of 100 miles per hour. Well, you just divide, right, and it would take 3 hours to get to you. So that's exactly what we're saying. Since light travels at a constant speed, it never ever varies, even when it gets stretched out. We can figure out the look back time if we know the distance. Remember back when we said that distance was one of the most important dang measurements that astronomers ever make? Well, here's kind of why, right? You want to know how old the universe is? You want to know how long it's taken from the most distant light to get to us? You've got to know the speed of light, which we know, and you have to know the distance to an object out there someplace. So if we know how far away the most distant things are, we know how long it's taken the light to get to us. We know the time. So we get some really important stuff out of this really simple equation here. So at the furthest distances we look, we're looking back to galaxies that formed at the very beginnings of the universe. Okay? If we look back even further still, we can see the hot matter that filled the universe soon after it began to cool. Now, don't answer the next question yet, because this is sort of more complex than it looks on the surface. Okay, so let's delve into this. How far can we actually see, and can we see to the actual beginning of time? Remember, the beginning of the Big Bang is the beginning of time, not just for us, but for everything in the entire known universe. So how far can we see? Well, unfortunately, not to the beginning of time. And I'm going to explain to you why here. Okay, so that's the answer there to number 12. We cannot see to the beginning of time. Now, how old was the universe when the most distant objects we can see formed? The universe, we can see objects. The most distant galaxies we can see were from when the universe was only about 1 to 2 billion years old. Now, that seems like a long time, but in the time frame of the whole universe, 1 to 2 billion years, that's pretty close to the beginning, right? But unfortunately, we're not seeing things at the actual beginning of the universe. The oldest things that we can see are about 1 to 2 billion years after the initial start of the Big Bang. Now, beyond that, there's a problem because there's really no objects that are shining brightly enough to see. Remember, the universe has to exist for a while before stars form and galaxies form, and we actually have light traveling through it. Okay? So you've got the answer there to number 12. Now, I gave you part of the answer here for number 13, but that's not really the whole picture. Okay? Why can't we see actually to the beginnings of the universe? Well, sure, right? There's nothing glowing at that time. There's not stars. There's not galaxies back that far that are shining light that we can see. But we've got a bigger problem than that. Okay. Now the more fundamental problem is that the early universe is so dang hot that it's completely opaque to electromagnetic radiation, i.e., light. There's your answer there to number 13. The reason you can't see to the very beginnings of time, the very beginnings of the universe, is because the universe is so hot that even light can't travel through it. It's opaque to light. That's what opaque means, right? Non-transparent. It can't get through, right? It cannot pass through. So no matter what, all we can ever see, the furthest we can ever see in time, is to a time when the universe became cool enough for light to travel through it. And that makes sense because seeing is perceiving light, right? Whether we're doing it with a computer, a CCD device, or our eyeballs, we're perceiving light with our eyes or those devices. So that's the answer there for number 13. Now, if you notice that picture there, I chose that for a reason because that's one view of the cosmic microwave background radiation. My cat has something to say to you there. I think he thinks I've been talking too long. You probably do too. We're almost done here. So, the cosmic microwave background radiation, a tremendous discovery. Very, very important, right? We theorize that this stuff exists, and then we find it, and this pretty much seals the deal for the Big Bang Theory, right? Like this is a prediction that the Big Bang Theory makes, that this background radiation ought to exist because the universe started out of this extraordinarily hot, dense state. So there ought to be some heat left over from this thing, and we ought to perceive it in the right region of the spectrum. And indeed we do, right? So what is the cosmic microwave background radiation? There for number 14. It is the glow of radiation that is the remnant heat from the Big Bang itself. Okay, now don't get hung up and think that, oh, if we keep looking further and further away out beyond the most distant galaxies, we'll see this stuff. In reality, it permeates the entire universe. It's everywhere we look. It's not just the most distant thing, it's all over the place. So this radiation, no matter where Penzias and Wilson pointed their telescope, it was there. It's everywhere. So the cosmic microwave background radiation has been traveling freely through space since the time the universe first became transparent to light, which is about 380,000 years after its formation. Okay, so it was quite some time after it formed. The temperature is currently 2.725-ish K. I think we already answered that one though. Okay. Now let's take a look at how we discovered this stuff. So one thing you have to understand is that on large scales, the universe looks isotropic, right? So in other words, what that word means is that the universe looks the same in all direction in all parts of space. So on large scales, we don't see any variation in this microwave background radiation. Or like no matter where you look in space, it's all the same temperature. You could phrase it that way as well for number 15. Okay, it's the same no matter which direction you look in space. Okay, that's pretty obvious to us. Now, recently, I don't even want to get into this, but there have been some calls to question about whether it's truly isotropic or not. And there's been some new research that says, well, maybe it isn't. And if it isn't, boy, that'll change all the rules. So a lot of things could change in the next decade or so with a lot of the information we even have here. So how do we discover this variation, this what we call anisotropy? In other words, like anti-isotropic, like not smooth in all directions. Well, we had to get some very, very detailed pictures. And the first attempt at that was COBE, the Cosmic Microwave Background Explorer of 1989. And COBE gave us this lovely picture here, which gave us the first inkling of what we assumed was going to be the case. There goes COBE, that the universe was at smaller scales not perfectly isotropic. There were some patches, some areas where there was some clumping. Okay, so what were those tiny variations there in number 16? Okay, the tiny variations. Oops, sorry, I'm not onto that page yet. So give me just a second here. But this is an image from essentially the leftover heat from the Big Bang itself when it first formed. Okay, so we've subtracted the uniform parts of the picture from it, leaving you just the hottest and coolest parts. So the variation is incredibly small. We weren't really truly how small the variation was until we sent up WMAP, named after, of course, Wilkinson. So the Wilkinson Microwave Anisotropy Probe. Boy, that is a mouthful, right? And we come to find out that the universe itself, the cosmic microwave background radiation, is similar in all directions to within 1 part in 100,000. Like, that is crazily isotropic, right? But these tiny little variations, and this is the number to answer to number 16 here, these tiny little variations in the density of matter and mass in the universe that we're detecting here, they're actually the seeds that are later going to become the galaxies and larger cosmic structures. So our question of how did galaxies form out of this essentially perfectly smooth soup of energy and matter? Well, if we look closely enough, we can see that variations in the cosmic microwave background radiation show us that it wasn't perfectly smooth. It was darn near, but there were tiny little variations, and out of that developed all the cosmic structure that we're going to later see that makes our universe the beautiful place that it is now. So that's the answer to number 16 right there. Now, if we know all of this stuff, we can actually figure out that the universe is about 13.7 billion years, give or take about 1% error. Now, that's a pretty finely tuned number there, isn't it? So what we're saying here is that if we know the present temperature of the universe, right, this cosmic microwave background radiation, and we know the present density of the universe, how tightly packed are all the galaxies and all the stuff that makes it up, we can then work backwards to calculate how dense and how hot the early universe was. And that's your answer there to number 17, right? If we know the current state of the universe, we can work backwards through some very, actually somewhat simple physics to calculate how hot and dense the early universe was. It's kind of similar to the same way that you would figure out, the temperature and pressure of the density of a gas in a balloon or a cylinder or anything else like that. Now, how hot and dense was it? If you run the clock backwards, darn hot and dense, right? It was way more tightly packed, way hotter than it is now. It's almost inconceivable how hot and dense the earliest universe had to be if this thing worked out the way that we think it has here. So this graph, it's a little difficult to kind of understand, but essentially what it's showing you is that the early universe had to be much hotter and much denser than the present universe. And if you look at the numbers there, at the bottom axis, we're talking about seconds. Seconds, not years, seconds since the Big Bang started. So starting over there on the left and moving to the right is the Big Bang proceeding forwards in time. And then temperature on the y-axis in kelvins, it's hotter at the top, tremendously so, and much cooler down there at the bottom. So if we start back on the left-hand side of the graph and move to the right, we see that the early universe was extremely hot and dense, okay? 10 to the 32 Kelvin. Now that's a lot hotter than when I was talking about somewhere around like 3000 Kelvin, right? Like that's crazy hot. So why did I throw that 3000, 3800 Kelvin number out there? Well, truth be told, that's the temperature at which recombination occurred. In other words, and we'll talk more about this, that's the temperature at which light was finally free to travel through the universe. So that's how far we can see back to. Now on your graph, if you look across that in seconds since the Big Bang, if you move to the right, okay, heading over there, the second blue line there where it says and it cooled and expanded, that's about the point of recombination, okay? So that's at about, I don't know, somewhere around there, 10 to the 12 seconds after the Big Bang. So somewhere around like 380,000 years since the Big Bang is what we're talking about there. So the universe, remember, is currently about 13.8 billion years old. Now that would on your this graph here, that would be about 10 to the 17 seconds. So that if you're looking at the far end there, it's at 10 to the 15. So a little bit further, the end of that graph there is essentially at present day. Okay, that's the end of the red line. And at that point, the universe is at about 2.7 Kelvin. Looking over there on the left of the graph, you can see it's just a little bit higher than 1. So there's the graph. Anyway, we'll continue more with this later. Good job for today. You should have answered right on up through number 17 on your questions there.